We are Team 20 with the Intercollegiate Rocket Engineering Competition. Now, my name is Maryel Gonzalez, and joining me today is Christopher Hayes and Giancarlo Lombardi. Now, the main objective of this project was to develop a rocket capable of going up to 10,000 feet above ground level, as well as carrying a 10-pound payload. Now, an additional component to this project is to develop an altitude targeting system. Now, the motivation behind this, pursuing this project was first and foremost to gain recognition for ourselves as well as our school. Now, the second one is to be able to compete against and then collaborate with other universities such as MIT, George Washington University, and of course international schools. Finally, we wanted to establish connections with leaders in the aerospace industries, of course, such as NASA and Orbital ATK. Now, this is an overview of our presentation where we start with the evolution of our design process, the design analysis of prototype construction and testing. Then we go into the conclusion and future work, project timeline, the division of responsibilities, and finally, the global learning aspects. Now I'd like to bring up Mr. Hayes. Stay there.
Okay, so we started with our conceptual designs. These are the three designs that we came up with. Our criteria for choosing between them was the drag, the complexity, the overall weight, and the manufacturability. Our final design ended up being this one here. You've seen this slide. And that's the overview of the components. The system level design challenges that we had to address. First we did the altitude targeting system is a big one. The actual airframe itself, the recovery system, and then for the purpose of this project, we're going to deliver a subscale version, which is half size of the real one. Okay. For the altitude targeting system, usually when there's altitude goals for a competition, they'll use adding or subtracting weight to reach it, and with simulations. We decided to go up above this and actually implement a targeting system which uses a computer-controlled algorithm to predict when to deploy a parachute during ascent to hit the altitude. So this is the actual physical functioning of the altitude targeting system. Right there you can see this is where the actual parachute is stored. Up here there's a charge mounted, and then there's a bulkhead on the bottom that actually is blown out. This is an analysis of the sizing of the parachute based on different forces it'll be exerted on it while at different velocities. Okay, the code portion of it, the way it works is the user inputs the actual target altitude, the rocket mass, coefficient of drag times area, and a delay that the actual system takes to deploy. What first happens is it gathers sensor data, and then it'll determine the y-component velocity, calculate the deployment delay, max altitude, and then once the max altitude of the program, if the parachute were to deploy, reaches the actual max altitude, if the parachute deploys. The equations we're using in this program are projectile motion with drag, and the motor we're using is a Cicerone, J330 actually, with a max thrust of 103 pounds, burn time of 2.26 seconds. This is the thrust curve and the cutaway view of what a solid motor looks like. Airframe, okay, so the dimensions of the subscale is 75 inches. So the materials we used were phenolic, resin, phenolic infused paper product. It has really good compressive and tensile properties, but it's brittle, so if it gets damaged, it breaks off really easily. So we wrapped it in fiberglass to address that issue. And the factor of safety ends up being about 69 with that and compressive loads. For fin design, our actual design, shape-wise, is designed to minimize damage from landing or any other events. We used G10 fiberglass as our actual material because it's extremely strong and resilient. We did air elastic analysis to determine when our flutter will occur or diversion will occur. The values we got with that are 878 feet per second and flutter velocity of 1,194 feet per second. That led us to choose a 0.093 thickness for the G10. And our actual max predicted velocity was 496 feet per second. So for the recovery system, this is how the rocket gets done safely. The sequence of events, first the air brake deploys to apogee. After apogee, the air brake is actually going to double as a drogue parachute. But just in case that none of that works right, we're actually breaking open the rocket the main parachute bay so that it wouldn't come in ballistic. So we actually have a reefed main parachute that's tied to the line, so that about 800 feet, the main parachute it has a cable cutter on it, and that will be cut, and the main parachute will deploy. Okay, so the avionics bay, this is the flight computer we're using. This controls everything, all the electronics, the Alta Spectrum Telemega. You can see our actual electronics bay down here, avionics bay. That number blue yellow thing is one of the charge caps. This is our wiring diagram. There's actually an onboard switch and an external switch so that the board and everything is completely removable, so you can take it to a computer. And I'll pass it over to Giancarlo.
So additional analysis was needed to determine what our predicted apogee would be with our design. So we used a commercial software called Roxen, and this allowed us to determine the approximate location of our center of pressure, center of gravity and center of pressure, and the relative location of both of these points, or these aerodynamic points, gave us the static margin, which determines the stability of the rocket. And the software was, again, to repeat, was calculated the flight and the drift of the rocket. So one of our main objectives was to determine how the weather would affect the actual flight of the rocket on the day up. The main parameter was the wind speed. So calculating for typical wind speeds and the maximum allowable wind speed at a commercial launch, we determined that the actual altitude would not be greatly affected by the wind. That concluded our design and analysis portion of our project, and we selected these components from online vendors to build the prototype. As Chris mentioned, we performed a fiberglass layup of the rocket, and we did this through fiberglass sleeves, which we imbued with epoxy resin and tightened with a heat shrink tube to remove any excess resin. Here is a picture of our motor mount tube within the rocket with considerations to the air brake bay, and then our removable avionics sled is shown here with the flight computer hooked up and the battery on the opposite side. And these molded connectors allowed for easy integration on and off the avionics portion. And this is a picture of our completed rocket placed before you. So once the rocket was built, we needed to ensure that the parachutes placed within the rocket would be ejected safely and completely during flight. So for this, we performed what are called ground injection tests. And so we first utilized the ideal gas law using black powder properties and determined that the air brake would need a 2.5 gram charge. And here is shown a very vigorous deployment of the air brake. So the charge remained at 2.5. And then the ideal gas law gave us a 1 gram charge for the black powder, but here it can be seen that the parachute did not fully exit the bay. So we doubled the gram to 2 grams. We doubled the charge to 2 grams, and it was shown that the parachute deployed safely. So then, having loaded the motor within the rocket, we launched with a thrust-to-weight ratio of 7 and a stability margin of 2, which is similar to our design stability margin. And here's a picture of a video of our actual flight test that didn't work.
The rocket is right there. Can't see it.
Rocket is placed here in the safely 100 feet away from the crowd.
Turn it on, that always helps. Okay, in 5, 4, 3, 2, 1, launch. They do that.
Okay. So as can be seen, our rocket performed perfectly on ascent. We achieved a maximum altitude of 2,300 feet with a maximum velocity of 480 feet per second. Of course, the actual attained altitude was not identical to the simulated altitude, and this can be attributed to this continuity or non-similarities between design and the construction, as certain protuberances in the airframe. Also, the final weight of the rocket was very similar to the design, was not identical as well. There was unfortunately a failure during the descent of the rocket where the lines of the two parachutes tangled and damaged the airframe. And this performed, the tangled lines pulled the cable cutter leads outside of the flight computer terminals, which prevented the actual main parachute from being deployed. So this parachute came down at a very high velocity, making damaging the airframe. The entire project gave the team a complete overview of the design and construction of a rocket and actually flew it. We gained experience in the design format that organizations such as NASA utilize with organizational structures such as PDR and CDR. Of course, the complete design experience took into account safety and timeline considerations, and provided us with lifelong learning that we will explain in detail with our teammate Maryel.
Thank you. Now, as far as future work is concerned, and as Giancarlo mentioned, the complete flight of the subscale led us to believe that future testing for certain components of the rocket need to be performed before putting them into the full-scale flight. Now, rocket is twice the size of this subscale here. So additional testing such as the shock cord lengths so that the tangling doesn't happen again. And of course, the continuous wireless communication between the Altus and on-site computers need to be implemented. Now, all members, as a precaution, are agreeing to apply their level 3 high-power rocketry certifications such that there won't be too many limitations on the rocket motor selection, as well as design features. Now, to your left are the division of responsibilities, and to your right, you can see the timeline. We can see that research, design, and analysis simulations took about 8 months to perform versus 3 months of the actual construction and testing of the design. Now, some engineering standards observed are, for example, the ones listed here. However, we saw that the encompassing standard, the all-encompassing standard, is in fact the National Association of Rocketry High-Power Rocket Safety Code, where level 1 and level 2 high-power rocketry certifications enabled us to see all the safety precautions and procedures, where launching and testing was done in a secure and controlled space. All launch sites, of course, had the permission from the FAA to obtain a restricted airspace. Now, the rocket design, construction, and of course the motor selection were all within the range of the certifications we obtained. So finally, the rocket was inspected and supervised by NAR-certified mentors. As far as our economic aspects, the space industry today, as well as the sounding rocket experimentation, is inspiring a new sense of, I guess, inspiration to reach the new frontier once again. So as the industry expands, new jobs are being created, as well as new technology improved. So wireless communication, medical devices for preventative measures, as well as water recycling and conservation systems are all being explored. And next, as far as our lifelong learning is concerned, as engineers, we can't really know everything, and our experience through individual certifications, our involvement with the NASA Student Launch experience, as well as our collaboration with experts, merchants, and distributors, led us to believe that theory can only take us so far. Later on, we actually saw the importance that safety is the #1 thing that all projects need to worry about. As far as global awareness is concerned, we see that the space industry, of course, has led us to new improvements in technology today, as the ones mentioned before, in medical fields and wireless technology. As far as global perspective is concerned, space exploration, of course, is bringing new innovation to technology. And for the testing and implementation of new technology, new emerging technology, is being brought up through new methods of implementing rockets. As far as global engagement, we had the opportunity to work with one of the most brilliant minds across our nation, but also this competition led us to collaborate with students internationally, such as those in Canada, Brazil, Puerto Rico, and Turkey. Finally, ladies and gentlemen, thank you for your time. This concludes our presentation.
Do we have any questions?
Is that going to fly again?
Yes, it can fly again. All we need to do is fix this portion of our rocket.
There's a tear on the fiberglass layer of the airframe that we have extra composite that we're planning on just patching it up and trying to keep it as smooth as possible, but it'll fly again.
Your subscale went to 2,300
Yes.
feet.
Yes.
What would you have to scale in order to get this to go to 10,000 feet?
10,000 feet.
Double the size.
Well, I mean, you would just use a bigger motor. We weren't trying to go for scale to 10,000.
Did the motor that you used in the subscale go to the height that you expected the motor would go to?
No, it was a little lower. We attribute that because if you see in the video, it cocked to the side.
Right.
We're thinking that's what brought it a little bit lower. But our altitude goal was mainly to test the systems, but not go to as high as we can or anything like
But
that.
your altitude targeting system couldn't be tested, correct?
What happened, actually, what happened is it got damaged on the first test, which was going to be a control test. So we're going to see how high it goes, and so that we could properly
adjust
set
that?
Yeah, so we could set the altitude lower so we know what force about the system is going to experience. But we couldn't fly it again that day because of the damage to the airframe.
Right.
So we are, the next launch coming up is in probably a couple of weeks. We're planning on testing.
On the 19th of December.
To do another subscale,
Yeah, to test the actual targeting system.
to target somewhere around 2,000 feet?
Right.
Exactly.
Right.
Well, like, probably a little more actually. I believe it was 2,000 feet over is going to be about 300 feet per second, which is our max limit. We're overshooting the actual altitude target of 10,000 by enough. So worst case scenario, we're still going to hit 10,000 itself. So it ends up being about 3,000 feet over on best case scenario.
And how does it scale? How big's the engine got to be to do 10,000 as compared to?
Yeah, I know.
So the motor we selected for our subscale, as you can see, has a 2.2 second burn time.
Yeah.
We actually did select a full-scale motor, and I believe it had about a 9-second burn time, and it was about 500 pounds force or so. And and the full scale, we have it at 50 pounds or so, so it will give us a thrust weight of 10, which is very desirable. It'll go really fast, really high. So. I believe you had a
The weight is about 8 times smaller than the full scale.
Since in the video you showed, it actually curved up immediately. You're not having flight controls at this point.
No.
It's just that.
It's
How
not-
confident are you that you have a good weight balance across the actual substructure itself? Balance between your rocket, your internals, your parachutes, and so forth. Because if you want 10,000, you need it straight as an arrow.
Oh, you're talking about the line of the rocket.
Yeah.
Yeah. Well, no,
Are
we
you
definitely-
shooting for a hyperbolic type of curve, or are you shooting up?
No, we want to keep it as
10,000?
straight as possible, and that's one of the reasons we're keeping the stability low. Because the lower stability means that it won't react to the wind as much.
Yeah.
So that's why we have the actual center of gravity is about right here, and then I think it was just 2 body diameters lower as the center of pressure. Weight, we make sure that as much as possible we can keep the weight centered throughout the rocket. The electronics are all on a sled, which is dead center as much as possible. So the mass.
One thing that would have helped you very good is the rocket doesn't have any markings outside. If you had any specific markings as to show which is left, right, bottom up, marked, that you can actually see it when you're capturing it, that level of inclination will actually tell you where to look for. right?
That is
What
true.
to actually structure or look at relocation or rotation within the structure inside. Right? So keep that in mind when you do your next shot, right? Mark it, look at rocket footage from NASA.
Yeah.
They don't mark it just because it looks black and white and nice. Right?
Right.
They have a specific measures when they're taking radio cam shoots of it, rotation, axes, and inclination and so forth. That's what the marking is for. So try to see if you can get a
Really high-
closer scope of how does it show you for the first
Right.
100 feet,
Yeah.
right? You can get that, then that gives you much more intuition and info to actually graduate and make the necessary changes for your latter flight. So don't expect it will be the next one. So I see like 4 or 5 until you get there.
Yeah.
Right.
Did you become licensed rocketeers? Is there?
We did go through
Yeah.
certain certifications. We have level 1 rocketry with NAR, and these two guys have level 2. So in order to pursue the full-scale launch, we actually have to get certified to level 3.
Like a driver's license, right?
Yeah.
Yeah, I'll show you it afterwards, but it says.
No, that's a global entry card, right?
Pretty much. It's good within the United States, but yeah.
And then just one more quick comment, it doesn't
Yeah.
matter whether it's on or not. I don't know what brought about section 9 in your report, the failure, well, the FMEA basically document. But thank you and get used to it. The FMEA, SFMEA, design, safety, and P process, if you're ever involved in manufacturing. Great habit to get into. So, the only report that had it, let's put it that way.
Thank you. Any more questions? Thank you.